That picture you've just seen should have looked fairly familiar, because that was a picture of a coordinate grid, a way of describing locations in space, giving one of these two-figure coordinates how far along the x-axis we are and how far along the y-axis we are. There's one more thing that coordinate grids are useful for. The last time we saw them, of course, we were drawing graphs with them in particular. There's one other thing we can use them for, and that is something called transformations. Transform as in changing. There are 4 different transformations . You need to know about. But all 4 of them are about taking a shape that's been drawn on the coordinate grid somewhere and changing it in some way. The first transformation you need to know about is a translation. Now, a translation is just a fancy way of saying moving. It's taking a shape, it's picking it up, and it's putting it down somewhere else according to a specific instruction. Translate shape A 6 down and 3 to the left, and label the new shape A1. Nice, clear instruction. Keyword there in the question, translate, actually being used, tells you that you are doing one of these movements. Translate, remember, just a fancy way of saying movement. We're then told which shape to focus on. There are 2 shapes drawn on the grid. Shape A is this one here. Nice, straightforward rectangle. 6 down and 3 to the left. There is a nice, clear pair of instructions on what to do with the shape. So you've got the keyword translate, you've got the instructions, and then you're told to label the new shape. Here is what we do. With the translate, it's like the whole shape has been picked up and put down somewhere else. The orientation of the shape, the look of the shape, neither of those will change. The shape will look exactly the same and it will still be the same way up. It will just be somewhere else on the grid. So what we need to do is we need to move it according to those instructions. 6 down and then 3 to the left. I'm going to choose one corner of the shape. Doesn't matter which corner I choose, but I'm going to pick one of them. And I'm going to pick this one here. And I am going to physically move that corner of the shape. We are told to move the shape 6 down and 3 to the left. So I am going to move that corner 6 down and then I'm going to move it 3 to the left. And I'm going to make it even more clear what I'm doing, partly for me, partly for somebody looking at what we've done here, by drawing in the jumps. So 6 down first and then 3 to the left. 6 down. So 1, 2, 3, 4, 5, 6 down. And then 3 to the left. 1, 2, 3. And that corner, bottom left, will end up here. I've got a choice now, and it's pure personal preference. This one, I can either just recognise that the shape will look exactly the same, and I can draw the original shape in its new position with this corner now being here. I can just look at the shape, count what it looks like, draw it in. I could even use something to help me draw it in. I could use a bit of this. Tracing paper, which is definitely tracing paper and definitely not greaseproof paper that I've just stolen from my kitchen. With a shape like this that's quite simple, it might be that we could just look at it and count it. With a more complicated shape, if it was a little bit more complex, if it had, say, some triangular edges in, say, we might want to think about using the tracing paper. We'll already have it. You might well have grabbed some for a rotational symmetry question, for example. It can be used here on these transformations as well. The alternative is I could look at each of the other corners and physically move each of the other corners as well. I could do this corner and move this one 6 down and then 3 to the left. And then I could do this corner and move this one 6 down and 3 to the left. This one 6 down and 3 to the left. And fill them all in that way and move the whole shape one corner at a time. Purely personal preference, doesn't matter which one you do, as long as the shape ends up in the right place. I'm going to choose to just draw the new shape in. So it's 1 wide, so we're going to be there, and 3 tall. It's going to look like this. I'm going to shade that in just to make that a bit more clear. And I'm going to label that according to how we're told to A1. What we've done is we've translated shape A 6 down and 3 to the left. We've labelled the new shape. Translate shape B by the vector and then 3 and a 4 in a weird bracket, one above the other, and label the new shape B1. Okay, so we've got that word translate again. That's telling us there's some sort of movement. And we're told what to do with the shape once we've moved it. We're going to label it B1. But what's this vector and this 3 and the 4? Well, actually, that's just a different way of writing the instruction. Let's have a look at that more closely. So this is what we've just seen. A 3 and then a 4 underneath it in this kind of tall bracket. Now, we were told in the question we've just read that that is a vector. In fact, it is an example of a vector. A vector is a pair of numbers that looks like this. Hopefully, you're looking at this and you're thinking, this is reminding me of something. Hopefully, it's reminding you of a coordinate. A coordinate is a pair of numbers next to each other in brackets with a comma in the middle. Something like, say, 2, 5, describing a particular point in space. Now, that is a coordinate. This is not a coordinate, but it is similar. It's like somebody's taken a coordinate and turned it on its end. Now, what a vector does is a vector is a different way of describing a direction. So a coordinate is a single point in space. A vector is a direction of movement. In fact, it is exactly the words we've just read for example, the first part of that question, the one dealing with shape A. We were given an across direction and we were given an up and down direction. A vector is just that, but turned purely into symbols. The number on the top tells us where to move left or right. And the number on the bottom tells us where to move up or down. So in this case, our left or right movement is 3 and our up or down direction of movement is 4. But how do we know which way we're moving? Are we moving left or right? Are we moving up or down? Well, it depends on the signs. Think about the way a coordinate grid is laid out. And look at left or right first of all. Read along the axis towards the right. We're looking at the positive numbers. We're starting at 0 in the middle and then 1, 2, 3, 4, 5, 6 and so on. So in fact, if it is a positive number, we are moving right. If we look down the left direction of the x-axis, the horizontal x-axis, we're moving from 0 to -1 to -2 to -3. So if that number at the top is a minus number, then we are moving to the left. Similarly with the y-axis, the vertical y-axis, the positive numbers are moving upwards. So if we are moving up, we have a positive number. And if we want to move down, the negative numbers are on the bottom half of the y-axis. So we are looking at a negative number for down. That's how we tell. Positive would be right or up. Negative would be left or down, depending on which of the two vector numbers we're looking at, the top one or the bottom one. This vector, for example, 1 and then -4. Well, the number on the top is the left or right number. It's a positive 1. If we're heading in a positive direction, we're heading towards the right. So it will be 1 right. And then the number on the bottom, the up-down number, is a -4. If it's a minus number, we're heading down. So we're going 4 down. So the direction given to us there, 1 right and 4 down. Second example, -5, -1. -5 on the top, a negative number on the top. Negative number in the left-right direction, we're heading towards the left. We're heading down the number line. So it'll be 5 left. And then 1 down on the bottom because it's a -1 for the up-down direction. Third example, 0, 6. Well, 0 on the top. So actually, in the left-right direction, we're not going anywhere. We don't necessarily have to write that down, because there isn't any movement. But in the up-down direction, we are moving by 6. Positive 6, so it would be 6 up. With no left-right movement, because of that 0 there. So just to finish up where we started, this particular vector, 3 on the top, that's a positive 3, so it will be 3 to the right. Positive 4 on the bottom, it's a positive 4, so it would be 4 up. 3 right and 4 up. So as we've just seen, this vector is just a different way of writing the instruction for a translation. It's just a way of giving a direction using purely symbols rather than words as well. So the 3 and then the 4, 3 on the top and 4 on the bottom. The 3, remember, is how far left or right we're going with a given direction according to the sign. And the 4 on the bottom is how far up or down we're going according to the given direction from the sign. So with a 3, we're going 3 to the right, and then with a 4 positive number, we're going 4 up. So we're going to take B, we're going to move B 3 to the right, and then 4 up. Could pick any corner to start with. I'm going to choose to do this one. I'm going to move this corner 3 to the right, and then 4 up. So that's 1, 2, 3 to the right, and then 1, 2, 3, 4 up. And that whole corner has moved to there. Once I've moved the corner, I can just draw in the rest of the shape. Or I could move the other corners just to check where the shape should end up. I'm just going to fill it in. I'm going to trust that I've done that okay. And it's going to go here like this. And that is B1. So we've translated again, but this time we've done it according to a vector, a numerical way of writing a direction rather than one using words. Second transformation we need to know about is that of the rotation. Kind of obvious what that does. It takes the shape and it turns it around in some way. The shape will look exactly the same. It won't change what kind of shape it is, but it will end up with a different orientation. It might end up upside down or on its side. The instruction for a rotation will be nice and clear, something like this. Rotate shape C 90 degrees clockwise about the point 1, 2, label the new shape C1. Let's unpick that a little bit. First of all, we've got this key word, rotate. That's how you know it's a rotation. You are told to rotate. Shape C, okay, fine. 90 degrees, right, there is a rotation. Standard rotations that you'll be asked to do, 90 degrees, 180 degrees, possibly 270 degrees. In theory, you could have any sort of rotation by any angle. They will tend to be the ones that we stick with. 90 degrees then, a quarter turn. Because we need to know how much we're rotating something by. But we also need a direction. It will either say clockwise or anti-clockwise. You need to check which way clockwise is. We'll look at a clock. It's to the right, in the right-hand direction. Look at the clock to check that though. Now what about this about the point 1, 2? Well, we'll come to that in a minute. First thing we're going to do, and then we'll explain what that is, we're going to grab something that we need in any rotation question, and we're going to grab this tracing paper again. And this time we are definitely going to use it. What we're going to do is we are going to trace around the shape. We're just going to trace it. Nothing fancy, we just need to trace the shape. There we go. Now we know that this shape will move a quarter turn and it will move in a clockwise direction. So it will move in this kind of direction. Problem is, where do we do the rotation from? Where is the pivot for the rotation? And that's what this final piece of information in the question is, about the point 1, 2. That is our pivot. It's what's called the centre of rotation. It is the point at which we make the pivot, so that the whole turn happens around that. And here's how we work it. We find that point on our grid, 1, 2. Well, it's 1 across and 2 up. So there it is. Right there, 1, 2. And we put our pencil on that point. We hold our pencil on. Our pencil now becomes the pivot point. The pencil is the pivot point now. I'm going to turn the tracing paper 90 degrees, that's a quarter turn, in this right-hand clockwise direction. And when I've got it to be a quarter turn, that's where my shape is going to go. So my new shape is going to go there. Moved quarter turn, notice, a quarter turn, there we go. And that's where I'm going to draw the shape. So I'm going to bear that in mind, I'm going to remember where that goes. And then I'm going to move my tracing paper out of the way, and I'm going to draw the shape in. And I can always put the tracing paper back just to help me. Okay. Should be doing this with a ruler, but never mind. C1, and there's our pivot point. So we've rotated shape C 90 degrees clockwise about that point 1, 2. That is our centre of rotation, the pivot around which we've had to turn the shape. And I've labelled the new shape C1. Key thing with the rotation question though, use the tracing paper. Third transformation we need to know about is that of the reflection. Again, fairly obvious what that does. What it does is it mirrors a shape in a certain mirror line. Again, the shape will look very much the same, but this time it will become backwards or upside down in some way because it's been mirrored. It will be back to front somehow. Nice clear instructions again. Reflect shape D in the line x equals 1. Label the new shape D1. If you are lucky, you will be given the mirror line. If you are not, you will have to draw it in yourself. In this case, we are being asked to draw it in ourselves. We are given the equation of a line. If you are asked to draw in the mirror line yourself, it will be a fairly simple, straightforward line to draw. It will be something like y equals x or y equals minus x. Those two fairly standard special cases that we have looked at before. Or it will be something like this, x equals a number or y equals a number. We've seen these kind of lines before. Think back to the graph stuff. X equals 1. That defines the line made up of all of the coordinates where the x part, that's the first number, is 1. The x is 1 is here. So in fact, x equals lines are vertical lines, and it would pass through the 1. That would be all of the coordinates where we're at 1 on the x. So I'm going to draw that in nice and clear. And I'm going to label that as x equals 1. There is my mirror line, x equals 1. Just to check, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and so on. X equals 1 drawn in as the mirror line. And now comes the reflect part, and to do that effectively, what I'm going to do is I'm going to grab my tracing paper again. And here's what I'm going to do. I'm going to put my tracing paper down on the page, and I'm going to draw over the shape. And I'm also going to draw over the mirror line. Because not only does the shape have to change its orientation, has to become backwards, it also has to now be, the new shape, has to be the same distance away from the mirror line, but on the other side. So I'm going to take my tracing paper, where I've traced the shape and I've traced the mirror line, and I'm going to turn my tracing paper over. As in physically turn it upside down. And here's the clever bit, this is why we've traced the mirror line. I'm going to line them up so that the mirror line is over the top of the one on the page. I just need to change this around, move this around on my page until they are at the same height. Well, there we go, I've lined the mirror lines up and the two shapes are now at the same height. And this is where my new shape is going to go. I could even trace over it now because I've turned the tracing paper upside down, and this is how tracing paper works. I could turn it upside down, trace over it very roughly, move my tracing paper away, and then just draw around the shape properly with a ruler. And there is my new shape. Label it D1. It's been mirrored, it's backwards from the orientation it had before, it is clearly mirrored, and it's also the same distance away from the mirror line as the original is. The fourth and final transformation that we need to know about is the enlargement. Now, enlargement, again, fairly obvious from the name, is about making things bigger, or in fact, making them smaller. Smaller, you ask? I'll explain that very shortly. Enlarge shape E by a scale factor of 3 about the point -6, -6, and label the new shape E1. First thing, word enlarge tells us it's an enlargement. Second thing, this scale factor of 3. Okay, that's worth looking at. The scale factor tells you how much bigger the shape gets. Scale factor 2 means the shape gets twice as big. Scale factor 3, 3 times as big. Scale factor 10, 10 times as big. Scale factor of a half, half as big, i.e. it gets smaller. That's why enlargements can sometimes be about making things smaller. But the scale factor tells you how much bigger, or in fact smaller, the shape gets. So in this case, scale factor 3, the shape is going to get 3 times as big. This edge, for example, is currently 2 wide. The new one will be 3 times bigger, will be 6 wide. It's currently 3 squares tall. The new shape, E1, will be 3 times bigger, will be 9 squares tall. But now the question is, where on the grid do we put the new shape? Do we just put it in any old place, or do we have to put it in a very particular one? In fact, we have to put it in a very particular one. And that's where this second and final interesting thing about the question comes from. This about the point -6, -6. Imagine, for example, a megaphone. So somebody speaks into a megaphone. Their voice starts off quite quiet, and then the megaphone makes their voice much louder. But the megaphone makes their voice louder in all directions. It doesn't just send it out straight forwards louder, it makes it louder in all directions. Yeah, a little bit like that picture. This is what the point given to us in the question does. The point that's given to us in the question is sometimes called the centre of enlargement. And what it does is it says not only does the new shape have to be however many times bigger, but the new shape has to be however many times further away from that named point than the original was. That will become clear as we start to draw this. So the first thing we're going to do with any enlargement question is we are going to notice which point we are given in the question, this about the point, and we are going to mark that on our grid. Well, the point that we're given in the question is this -6, -6. So let's mark that on our grid. That's -6 along the x and -6 along the y, and that is there. Now the first thing we're going to do is we're going to focus on this shape that's already drawn on the grid, this E, and we're going to see how far away that shape is from the point we've just marked. I'm going to choose this corner here. Doesn't matter which, could be any corner, but I'm going to choose that one because it's going to be easiest to do. And I'm going to count how far away this corner is from this point. So it is 1, 2 left, and then 1 up. 2 left and 1 up. Our scale factor is 3. So this shape is going to get 3 times bigger, but it's also going to get 3 times further away. 3 times further away from that marked point. So instead of being 2 right and 1 up, it's now going to be 6 right and 3 up. And that corner, the bottom left corner of the new shape, is going to be 6 right and 3 up away from this point, 3 times further away. So I'm now going to draw in those jumps and work out where that matching corner, that corresponding corner, needs to be. So we're going 6 to the right, that's 1, 2, 3, 4, 5, 6, and then 1, 2, 3 up. And the corresponding corner of the new shape is going to be there, 3 times further away. The original corner that we were looking at, 2 right and 1 up. The new one, 6 right and 3 up, 3 times further away, because we're looking at a scale factor of 3. Now I could choose to move the other corners in that way if I wanted, or I could just draw in the shape as I know it should be. I'm going to choose to draw in the shape. If you prefer to count the other corners into their new positions, please by all means feel free. The original shape was 2 across the bottom. The new one is going to be 3 times bigger, so it's going to be 6 across the bottom, starting from here. So that's 1, 2, 3, 4, 5, 6. Nice and neat across there. The original shape was then 3 squares in height. The new one is going to be 3 times bigger, so it's going to be 9 squares in height. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, right up to the top of the grid there. And I should just be able to draw in that diagonal line there, nice and easily. And there it is. It should be 3 times longer. Hopefully it will be. And there is my new shape. I'm going to label that as E1. So the new shape, 3 times bigger, but also 3 times further away than that named point. There's an interesting thing we can do with enlargement questions once we've drawn in the new shape, and it's a useful way of checking that we've got the enlargement correct and in the right place. You don't necessarily have to do this, but it is worth a check, whether you draw it in or whether you just test it out without drawing it. It's useful as a check, and it's also useful for something else which we'll come to shortly. What you can do is you can grab a ruler, and you should be able to draw a line from about the point that we marked to pairs of matching corners. So I should be able to draw in this as a straight line, and it should be able to pass through all 3. So there's that first one, the 2 bottom left corners, and that point there. I should be able to match up the top corner in each case and join it up to that -6, -6, like we've done. And I should be able to match up these 2 right-angled corners and that point as well. And look at that, all 3 work. Key thing though, they all meet those 3 lines at this point down here, the -6, -6, and that's important for something in a few moments. Now in each of those 4 questions you were required to do basically the same thing. Carry out a certain transformation, either a translation or a rotation or a reflection or an enlargement according to the instructions that you were given. It is possible that a question could be phrased the other way round and give you 2 shapes on a grid and ask you to describe in full the single transformation that has taken place. Now if you're asked to do that, it will again be either a translation or a rotation or a reflection or an enlargement. And working out which one it is usually fairly simple to do. If the shape has moved on the grid but still looks exactly the same, it's not turned upside down or backwards or anything like that, if it's just moved on the grid, then it is a translation. And if you are saying it's a translation, then you have to give the word translation and a direction. You may be able to give the direction as words, you may have to give it as a vector, but you have to give the word translation and a direction. If you look at the pair of shapes and you feel that one is rotated in some way. It's turned on its side or it's upside down, but it's not mirrored. They're not at the same kind of level in space. Then you must give the word rotation, a direction either clockwise or anti-clockwise, an angle as it turned 90 degrees or 180 degrees, and you must give the pivot point, the center of rotation. How do you find that? Well, you grab some tracing paper and you test some points, and you keep trying pivots until you find the one that works. Nothing to it, nothing fancy about that, just keep trying, you'll find one that works. Quote that point. So the word rotation, a direction clockwise or anti-clockwise, the angle that's been rotated by, and that pivot point that you are going to find by trial and error. If, however, you look at the shapes and you feel that one is the other reflected, is mirrored in some way, then you need to say it is a reflection, so you need to give the word reflection, and you also need to give the equation of the mirror line. That's probably the hardest to do because you're going to have to bring in your graph stuff, but it's likely that it's going to be something like y equals x, or x equals a number, or y equals a number. Remember, x equals a number are vertical lines, y equals a number are horizontal lines going across the page. The easiest of the four transformations to spot will be an enlargement. If the shape has obviously got bigger or smaller, it is clearly an enlargement, in which case you need to say that it is an enlargement. You need to give a scale factor, so just count the sides of one, count the sides of the other, and then work out how many times bigger or smaller it's got. If it's got smaller, then you're talking about something like a half, or a third. If it's got bigger, you're talking about something like 2 or 3 or whatever. And you also need to give that starting point, that centre of enlargement where everything's fanning out from. To find that, we'll just do the ruler thing. Draw in the lines from the corners. Find where those lines cross. That's your centre of enlargement like we've just done. That's why it's important.